Broadband MMW ATSA design. The geometry of the ATSA antenna is shown in Figure 7a. The antenna was designed on RT/Geroid 5880 laminate having a dielectric constant of epsilon r equals 2.2 and a thickness of 0.254 mm. The top and the bottom plane conductors form an antipodal feed arrangement, enabling the ATSA antenna to exhibit excellent broadband characteristics. The tapered ground plane is obtained by cutting a half ellipse with the radii of the major axis and minor axis, R1 and R2, respectively. The top plane and the bottom plane conductors are tapered according to the guideline given in Ref. In order to reduce backward radiations, the linear corrugation is designed and optimized by executing several full-wave simulations using the CSD Microwave Studio computer program. The optimized parameters of the ATSA are listed in Table 3. Optimized dimensional parameters of the proposed antenna. Geometry of ATSA: A. Rectangular configuration, B. Lens-loaded conformal configuration. The geometry of the proposed conformal ATSA is shown in Figure 7b. The ATSA element is designed over a low-thickness flexible substrate, which allows us to round the antenna element over a cylindrical surface. We selected a cylinder of foam material to preserve the electrical characteristics of the designed antenna. The radius of the foam cylinder is 12 mm. In order to enhance the gain, the ATSA is loaded with a half-spherical dielectric lens with a relative permittivity of epsilon r equals 2.2 and optimized radius, RS, of 32 mm. The length, LC, of the conformal structure is the same as that of the nonconformal antenna, which is equal to 32 mm. The calculated performance parameters of the proposed antenna structures are discussed in the following subsections. Results and discussion. The ATSA of the conventional rectangular shape was first optimized to exhibit a -10 dB bandwidth over a wider frequency spectrum. In the conformal antenna design, the radius of the foam cylinder is optimized for a minimum realizable value without compromising the electrical performance of the original ATSA. Finally, a dielectric lens is introduced toward the end-fire direction of the conformal ATSA, and S-parameter values are calculated. The S-parameter curves of the ATSAs having rectangular, conformal, and lens-loaded conformal configurations are presented in Figure 8, showing S11 values less than -10 dB from the 14.8 to 40 GHz frequency band. All three curves presenting the reflection coefficient performance of different ATSA configurations are found to be in close agreement with each other. The rectangular-shaped ATSA radiates toward the end-fire direction with E and H plane pattern symmetry. Figure 9a and b compare the normalized radiation patterns of ATSA's rectangular, conformal, and lens-loaded configurations at 28 and 38 GHz, respectively. The conformal ATSA without a lens exhibits almost the same radiation pattern as the rectangular ATSA at both frequencies, except that there is a shift of 4 degrees in the H-plane pattern. The ATSA configurations without a lens present an average 3 dB beam width of more than 40 degrees in both planes. On the other hand, the lens-loaded ATSA finds a 14 degrees shift in the H-plane beam with a 3 dB angular width of 12 degrees. The introduction of the dielectric lens toward the end-fire direction enhances the gain of a conformal ATSA due to the focusing of the radiated field in space. The diameter of the dielectric lens is optimized by several full-wave simulations. The results presenting a parametric study of gain versus frequency against different diameters of dielectric lens are shown in Figure 10. A significant improvement, i.e., more than 10 dB, in gain parameters is observed by increasing the radius, RS, of the dielectric lens up to 32 mm. Table 4 presents the comparison of the radiation characteristics among the three configurations of the ATSA. Comparison of peak gain and radiation efficiency among the MIMO antenna systems. Reflection coefficient versus frequency of three different configurations of proposed ATSA. Copolarization radiation patterns in phi equals 0 degrees, H plane, and phi equals 90 degrees, E plane, cuts at, a 28 GHz and, B 38 GHz. Gain versus frequency against different radii of dielectric lens loaded toward end-fire direction of ATSA.